Welcome back to the deep dive. Today we're tackling, well, what's maybe the single most stubborn, expensive problem for large language models: scaling the context window.
It's a huge bottleneck.
Yeah, think about the tasks we want them to do, like understanding really long documents, massive legal briefs, or, reasoning that needs info from hundreds of pages back.
For that kind of depth, you need a huge memory, right? A context window heading towards that million token mark.
But the way these LLMs are built, making that memory bigger just leads to these prohibitive compute and memory costs.
Right. People have tried lots of things, extending positional encodings, modifying attention itself. Yarn is one example.
But they keep hitting this fundamental wall, don't they? Even if you make the computation better, maybe going from n squared to n.
You still have n tokens. If n is a million, you still have to process a million inputs. The overhead is just still massive.
So what's interesting here is the approach taken by researchers from Tsinghua University and Zipu AI. They sort of sidestepped the token count issue.
They did. They introduced this framework called Glyph. Instead of tweaking the text pipeline, they came at it from, well, a totally different angle. Visual context scaling.
Okay, visual context scaling. Let's unpack that for you, the listener. Our mission today is to really understand this counterintuitive idea, turning text into an image to get data compression, but still keeping the performance.
And that's really the core idea. Glyph basically says, stop processing text tokens. They're not very dense. Instead, render these ultra-long text documents, books, code, whatever, into compact images.
So you replace the text LLM with a vision language model, a VLM, that's trained to read these compressed text images.
That's the plan. The VLM works on these visual renderings, these glyphs, as they call them.
But how does that increase density? Wouldn't processing images usually be more computationally heavy?
That's a fair question. Think of it like this. A standard text token is maybe a word or part of a word.
Right.
A visual token, the input chunk the VLM sees, could be like a little picture of a whole paragraph or maybe several lines of code.
Ah, I see. So each visual chunk carries much more original text information.
Correct. Each visual token acts as a dense carrier for maybe dozens of text tokens. You're condensing information spatially.
And this leads to quantifiable compression.
Yes, the paper reports achieving 3 to 4 times token compression for long sequences.
3 to 4 times. Wow. Can you give an example?
Sure. They use the novel Jane Eyre. It's about 240,000 text tokens.
Okay, way too big for a standard, say, 128K context window LLM. You'd have to chop it up.
Right, which breaks long-range understanding. But with Glyph, they render that whole 240,000 token novel into about 80,000 visual tokens.
So it fits. The whole book fits inside a 128K VLM because it's operating on the compressed visual form.
That's it. And this compression directly impacts efficiency.
How so?
Well, the researchers found it leads to roughly 4 times faster prefilling and decoding.
4 times faster answers from long documents.
And about 2 times faster supervised fine-tuning, or SFT training. So serious time and compute savings across the board.
Okay, but it can't be as simple as just taking a screenshot, right? The VLM has to be really good at reading these images.
Absolutely. And that's why Glyph isn't just rendering, it's a whole systematic 3-stage framework.
Makes sense. What's the first stage?
Stage 1 is continual pre-training. This is all about making the VLM robust to how the text looks.
So not just one standard font and layout.
No, definitely not. They train it on diverse visual forms.
Huh.
Think of formal documents, messy web pages, dark mode interfaces, even structured code.
So it learns the text regardless of the presentation.
Exactly. This involves specific tasks, OCR obviously, but also interleave language modeling, mixing text and image inputs, and generation tasks, like predicting missing parts of a rendered page.
Okay, building visual robustness. What's stage 2? You mentioned it gets novel here.
Stage 2 is the LLM-driven rendering search. This tackles that crucial trade-off.
The trade-off being?
Between compression and accuracy. If you shrink the text too much visually, make the font tiny, or lower the DPI, you save space, but the VLM might not be able to read it accurately.
Right. But if you keep it large and clear for high fidelity, you lose the compression benefit.
Precisely. So you have all these rendering settings, DPI, font size, page layout, colors, alignment, creating a configuration vector. Let's call it theta.
Yeah.
How did you find the best theta?
There must be thousands of combinations.
They don't guess. They use an LLM itself to drive a genetic search.
A genetic search, how does that work?
Think of it like rapid evolution. The LLM evaluates different rendering configurations, different genomes on test tasks. It checks both the compression ratio and the task performance.
And it selects the fittest ones.
Yeah, the ones with the best balance of high compression and high accuracy. These are then used to generate new, potentially better configurations. It automatically explores this huge parameter space.
To find that optimal setting, a theta that gives maximum density without hurting performance too much. That's clever, because the best settings probably depend on the VLM itself.
They certainly do. It's not intuitive. Once they find this theta, they may move to stage 3, post-training.
Which involves
The more standard refinement steps. Supervised fine-tuning, using those optimal rendering settings, and then reinforcement learning specifically, they use something called Group Relative Policy Optimization, or GRPO.
Okay, fine-tuning with the best visual representation. But you mentioned a guardrail they put in place here.
Yes, during post-training, they add an auxiliary alignment task. It's an explicit OCR task.
Why add OCR again here? Wasn't that covered in pre-training?
It serves a slightly different purpose here. It acts as a constant quality check, specifically enhancing the model's ability to recognize the fine-grained text within the images.
Ah, so it's reinforcing the link between the visual block and the actual sequence of characters.
You got it. It ensures the VLM doesn't just get the gist, but maintains the fidelity of the original text, character by character, as much as possible.
Okay, that makes sense. So the 3 stages build up the capability. Now, the bottom line. How did Glyph actually perform? How did it stack up against, say, well-known long context models like WEN38B or GLM490 Chat1M?
The results are quite compelling. On standard benchmarks like Longbench and MRCR, Glyph achieved comparable accuracy to these text-only models.
Comparable accuracy, but using fewer tokens.
Significantly fewer.
Yeah.
Remember that 3-4x compression. It achieved this accuracy using 3 to 4 times fewer visual tokens than the text models use textual tokens.
Can you give the specific numbers from the benchmarks?
On average, they found an effective compression ratio of 3.3x on Longbench and 3.0x on MRCR.
Okay, so similar performance, much less input data for the model to process. That implies a scaling advantage, right?
It does. Think about expanding the context window. If a text model goes from 32K to 64K, it gains 32,000 tokens of capacity.
Straightforward.
But if Glyph's VLM context expands by 32,000 visual tokens, and it's running at, say, 3x compression.
That's like gaining capacity for 96,000 original text tokens. It's leveraged.
That's the leverage effect. A smaller increase in the VLM's nominal window translates to a much larger increase in the effective length of text it can handle.
And this explains why the results showed Glyph degrading more slowly as the input length increased.
That seems to be the mechanism. It's always dealing with a relatively smaller compressed input compared to text-only models tackling the raw sequence length.
Did they push this compression idea even further?
They did. They explored more aggressive compression settings, really trying to stretch the visual approach.
And what happened when they cranked up the compression?
They tested an effective 8x compression ratio.
8 times.
Yeah. And even at that rate, the model showed potential to handle tasks at the 1 million token level of original text. They benchmarked this specifically on the MRCR task, scaling context lengths from 128K up to 1024K.
So reaching that million token effective context seems feasible with this visual compression route.
It provides strong evidence that boosting token information density rather than just fighting algorithmic complexity is a viable path forward for scaling.
It really is a completely different way to think about the problem. Instead of optimizing the attention math, optimize the information content of each input unit. Quite remarkable.
It is remarkable engineering. But we should also touch on the limitations the researchers themselves highlighted.
Okay, what are the catches?
Well, first, the whole process is quite sensitive to those rendering parameters. Getting theta wrong means performance can drop off significantly. That LLM-driven search is crucial, but it highlights a sensitivity.
Makes sense. What else?
The other main challenge they noted is around low-level OCR fidelity.
Meaning the VLM isn't perfect at reading every single character correctly from the image.
Especially when the text isn't typical prose. It's great at understanding paragraphs, the flow, the structure, because that's what it's trained on visually.
But it struggles with
things that are distributionally sparse text patterns it hasn't seen much of.
Yeah.
The key example they gave was recognizing rare alphanumeric sequences.
Like UIDs, those long random-looking IDs you find in logs or databases.
Exactly. Long strings of seemingly random letters and numbers. The VLM, trained on meaningful language blocks, can apparently struggle to reconstruct these sequences perfectly, sometimes misordering or misclassifying characters.
Ah, so if the task requires pulling out a very specific non-linguistic code like that with perfect accuracy.
The visual compression method might be slightly less reliable than a traditional text model that processes character by character.
That seems like a key area for future work then.
Yeah, it is. The researchers point to improving this low-level text recognition, essentially making the visual reader as accurate as a character model on precise non-language data as a critical step to push this visual compression idea even further.